All right, we're good. Milo, how are you doing?
I'm good. Yeah.
Nice. So I just have one big question for you.
Okay.
What is quantum computing?
It's when you make a computer that fundamentally runs on quantum mechanics, and like already, like the computer like you have in front of you that's recording audio, like it's using transistors, and the transistors are using quantum effects, kind of. So it already is like slightly a quantum computer, but in the quantum computers people are talking about when they say we want to build a quantum computer, it's one where not only are the parts quantum, but the way it processes information is quantum. So like you could sort of imagine that all the components on the computer on your laptop are totally classical, and there is no weird quantum effects, and just like you have bits, and then you have like different logic gates that tell you how these bits interact with each other. But on the quantum computer, you can't pretend the world is classical. Like the quantumness is in your face. It's in the way the computer processes information.
Yeah.
It's a quantum computer.
And what's the benefits of that versus having a classical computer?
The benefit is that a quantum computer can do things a classical computer can, and so the way people first made this observation, like there is this famous talk by Feynman, where he was musing about how there's these effects and these interactions in quantum mechanics which are really hard to simulate. Right? So you have physicists who have their computers and they're trying to simulate like the way different molecules are going to interact with each other. These different small quantum systems are going to work, and they can't do it. The computers can't simulate it. And so on the one level, this is like a downside. Like this is bad. We can't simulate our physics. This is like holding up scientific progress. On the flip side, you find that this means that quantum physics, these small things we can't simulate, are doing something our computers can't. Right? If our computers can't simulate them, the physics can. Right? Like here's a really quick way to tell how two molecules interact. Just make the molecules help them interact. Right? They're going to interact in some way. You're going to get output. And so in a way, the fact that quantum mechanics is hard to simulate means it's doing something we can't simulate. It means it's doing something sort of beyond classical power. So that's how you know that quantum computers can do something we can't.
Right. And it does that using the qubit, but can you kind of describe in a very first simplistic and then as complex way as you can with a qubit, with like superposition, and I know sometimes people use like some sort of like vector where it can be like up or down. Can you describe that?
So if you want to talk about computers like abstractly, you want to make some claim about how computers work, you don't have to talk about bits and how bits interact with each other. You can sort of make general claims like they process information, they take inputs, they spit out outputs. You can say things about computers without talking about bits. And similarly, you can talk about quantum computers without talking about quantum bits, qubits, right? And so the most simple types of computers rely on qubits. Not all quantum computers do. Like the sort of quantum computing I do typically doesn't rely on qubits. And so in my eyes, like a qubit is just a nice metaphor for like the simplest piece of quantum information. Like a bit is like it's either on or off. There's either current flowing through a wire or there's not. And similarly, a qubit is kind of the simplest piece of quantum information.
How powerful are like the most powerful quantum computers right now? Because I know the most powerful classical computers have like billions of transistors in them.
Yeah.
How's quantum looking like?
Well, if I want to say the optimistic number, right, like the PR line, you would say, a couple hundred. Right now,
okay.
A couple hundred. So this is like the most optimistic way of looking at things. But there's an issue, which is that you can't use the qubits we made right now. Right? Like you have like it's a single like unit of quantum information, but like the ones that have a couple hundred qubits, they're stored in these very, very noisy ways. Like for instance, you'll have like some atom, like rubidium. I guess that's an atom. You look it up on the periodic table, and it's stored in the position of a single electron. Right? It's either is it in this orbital or is it in that orbital? It's like which orbital is it? And what is the position of this individual electron? And it's a very, very small thing. It's a single electron. And so if someone like turns on a microwave in the room next door, it'll like mess it up, it'll jump, right? And so the way you protect it is you put it in a fridge, you make it very, very cold, you do your best to protect it from the environment, but it's still noisy.
Yeah.
And so you have a whole bunch of very bad qubits, a couple hundred of them. And so then people do this, this form of error correction where you put in a whole bunch of bad qubits together, and you get a single good qubit out of it.
Okay.
And then, but that process, if you take in like 60, qubits to make one good qubit. And so now your couple hundred turns into 5, right? Because you took a whole divine qubit to take one qubit. And so I would one way of looking at it is with a couple hundred qubits. But if you want to actually look at the logical qubits, the ones you can use for computing, it's like 10. Like it's more, it drops down a lot.
What can we do with just 10 qubits?
You can learn how quantum computers work. Like people do things and they say, wow, this is what interesting data we're getting. Like we're finding out how our computer works and we're learning more about it that's going to help us build things in the future.
Yeah.
And so physicists care about the results that are coming out of these 10 qubit states. But if you're someone who's like practically minded, you're saying like, I have a computation problem, like I run like a finance company and I want to use a quantum computer to crunch our numbers. Mm-hmm. Like you will not care. Like no one who has concrete computation problems is going to quantum computers to use them to solve them. Yeah. Right. That's not where we're at.
Yeah, I was hearing about the I forget the exact technical name, but the finding the prime numbers of a very large number.
Yeah.
And I heard that you need about 100,000 qubits for reference to solve a problem like that.
Yeah.
But now we're only working on scales of 5.
Yeah.
Okay, gotcha. Yeah. And to condense those 100 qubits into 5, is that quantum entangling those 20 qubits into 1, or is that some other process that is allowing that to happen?
It's a really subtle process, and so it's this form of like quantum error correction, right? Like this, how do you take a whole bunch of bad qubits to make one good one? Which is actually like that's what I do. Like I spend a whole bunch of time thinking about these sorts of ways of doing it, because the hope is that like on one side there's people trying to make as many qubits as you can and make them as good as you can. And on the other hand, you have to get better and better at squeezing out good qubits out of it. And so typically like it is some sort of complex entanglement between a large number that makes these like weird wave functions that are somehow more protected from the environment than the individual ones.
And is that where topology comes in?
Yeah.
Is it topology of the wave system? Or is it something else?
Yeah, so like that wave function is sort of described in a way by topology.
Well, how about this? Why don't we start by describing the wave function, and then you can get into topology, and you are more than welcome to go in as in-depth and as complex as you go.
Yeah.
Just have fun with it.
So, I mean, like, what is a wave function? Like, if you describe, like, a bunch of, like, a classical system, right? Like, you describe, like, just, like your position, right? There's going to be just, like, some way of describing it, some way of describing the state of a classical bit, which is the positions of all of its components. In quantum mechanics, things don't have well-defined positions. They sort of spread out as waves. And so if I want to describe you, I don't say all these positions. I say all these spread out or wave type things. I describe your wave function. And so the wave function is how you describe something in quantum mechanics. It's described by a wave function. And so when you have some big complicated wave function, I say it's some big complicated state, right? I could just use the word state. It's just a way for those qubits to be.
Yeah, and so where does your work tie into all of this and quantum computers? Like, what exactly is it that you're researching and doing?
So people have this problem. They find that even when they make thousands of qubits, they only actually get like 20 out because you have to put a whole bunch together. Or even like the original problem, if your qubits are noisy and you don't have any ways of putting them together, you just have a whole bunch of bad qubits. And no matter how many bad qubits you make, you're never going to have a good computer. And so people say you have to solve this. You have to solve the issue of having a whole bunch of noisy bad qubits. And the answer typically is to use a math of topology. And so topology it's a math class. If you are a math major at a university at UC Santa Barbara, you will take it like in your second or third year. And there's a real way in which this math helps you protect quantum information. And so that's kind of a topological quantum computer, a quantum computer you use making topology. And this fits into two major branches. There's one branch which is, let's find some material which is topological in nature, right? So these materials exist and are in a real sense described by topology. And
what do you mean by that? Like, can you give an example?
What it means, so if I want to give you an example, I would say like a sheet of graphene. So there's a bunch of carbon atoms arranged in some flat plane. You make it very, very cold. You pump a huge magnetic field Correct. It's like 5 Kelvin is the temperature, so that's very cold. 15 Teslas is magnetic field. That's very big. And you start getting some weird stuff. Yeah. And that's topological quantum at that level, right?
Okay. Yeah.
And so that's an example. And I mean, before I can describe what it means for something to behave topologically, I'd have to like say, what is topology here in this little math class? But yeah, I mean, when you describe it, it's gonna use that math, right? Like you're gonna need it, and you're gonna use subtle concepts from that math. And so that's topological quantum computing. Mm-hmm. And so either, like I said, it's split into two main branches. One is you find a material, you do like this sheet of very cold, very big magnetic field graphene, and you make a computer out of that. Like this is your computer chip. Like your computer chip is really cold graphene. Yeah. And then you build it out of that. Or and this is kind of cool insight. Okay. You start with a just normal quantum computer. Okay. So you built it, you have a whole bunch of bad qubits. What can quantum computers do? Quantum computers can simulate quantum systems. They can simulate other quantum systems. You use your bad quantum computer to simulate a topological quantum system. Okay? You simulate a topological quantum system. Topological quantum systems are resistant to errors, like I just said. Like that's how you build them. And because you simulated something resistant to errors, you become resistant to errors. It's like Kirby who eats someone else's power. It's like you simulate the topological system and you become error resistant. You inherit that. Yeah. And so that's what you do. Like, and so like on all your qubits, like in this all your rubidium atoms of their electrons in different levels. Like you're simulating what would happen if you're on a graphene sheet at really low temperatures and high magnetic field, and you're stealing its error resistant properties. Mm. And so, from a physical perspective, these are very, very different processes. For a mathematician, it's like, well, mathematically, it's the same thing going on, right? Yeah.
No, but the simulation has limitations, right? Yeah. Because if you only have 5 usable qubits, then I imagine you probably can't simulate 10,000, right?
So, what's cool is the simulation is not being done with the 5 usable qubits. The simulation is done with your bad qubits.
Oh, I see.
And the point is, when you simulate the system, your qubits become good qubits because your big system built out of bad qubits will simulate a smaller topological system, and so the smaller topological system is going to have 5 good degrees of freedom, which are actually protected from errors. Yeah. And so that's how you do it. And so you can really simulate big topological systems with a whole bunch of noisy qubits.
Yeah. Yeah, so this is what you're going to Caltech for next year, right?
Yeah, so I'm going to grad school at Caltech I guess I'm in the math department, but my advisor, he's taken 2 physics students before and 1 computer science. So it's never taken a math student. Mm-hmm. So it's really taking mathematical physics, thinking about how does information work in these topological quantum systems.
Yeah, and is it, like, do you do a lot of coding, like, with your work, or is it mostly just kind of pure mathy in that sense?
What people talk about, like what's coding is subtle, right?
Okay.
So if you want to program something on a quantum computer, at the current level, you're going to have to specify like a bunch of rubidium atoms with electrons at different levels. Like what are their positions at different moments? Like you have to like rotors moving those around. Mm-hmm. Like where exactly do you want to move them? And then you're also going to specify like you're going to be like shining lasers at them to implement quantum case. Like how strong do you want your lasers to be? When do you want to time them? Like, it's a really concrete process. It's really very, very grounded process, and there's no high-level programming language for it. And the reason you don't have a high-level programming language is that every month the computer changes, and so you have to rewrite the language, and there's no point. Mm-hmm. Right? So it's very, very tough thing to do, and a very expensive experiment to do it. And so every time you kind of run a new error correction algorithm on one of these computers, this is a big endeavor, and you like get a paper out of it, right? Mm-hmm. So it's like every time that you write up your code, you like publish it and say, look, I coded this thing. Yeah. And the fact that you coded it and it ran as expected, it's like, is the result that you're publishing? Yeah. Right. So in some sense, like I'm part of this coding process, like I'm part of coding a quantum computer, but like I'm on the more abstract side. Mm-hmm. Like I haven't done any sorts of experiments yet, but one of my colleagues who was at Caltech, he's a postdoc, Nathan and Tentisavadakarn, he went to some lab and said, great, I have a new error correction algorithm that you simulate this specific topological quantum system. You should let us do it. They said, great, let's do it. And so then like they got a group of like 30 people together, and they spent like 6 months, and then they simulated it, and they saw that it sort of worked, and then they got a paper, and so they all kind of worked together to code it.
So being on the more theoretical side, are you working a lot with like the quasi-particle that makes topological quantum computing work? Is that...
Yeah, so here what you're referring to is the fact that there's these things in topological quantum systems called quasi-particles. And so the word quasi and quasi-particle means that it's something that behaves like a particle, but is built out of a whole bunch of smaller degrees of freedom. So for example, like a wave on the ocean it's not a bunch of water molecules moving, right? It's a whole bunch of molecules going up and down all at once. But you have this sort of emergent thing, which is a wave moving. Like you say that's a wave, like which water molecules are in it is changing all the time, but it feels it's this emergent thing that moves. And similarly, quasi-particles are built on a whole bunch of smaller things, but you see it as like this bigger thing coming out of it moving around. And so this notion of emergence is, in a way, I'm already talking about it. Like when you have a whole bunch of noisy qubits that go to make a few really good ones, that's emergence, right? Like you have like one good like little wave being built out of a whole bunch of noisy molecules.
Gotcha.
And like you can see down the ocean, like if it's a really rough night, your water is sloshing up and down, you have a whole bunch of really noisy water. But the big wave is moving at a nice constant, right? That's even in the storm, that's clear. And so that's how what you're making. Like you're in a storm, which is the environment, and you're getting that big wave out of it. And so that's the emergent property.
And that's how you're able to work with something that doesn't really exist in some sense, right?
Yeah, because it's built out of all these, and you see it move.
Yeah. Yeah, I guess going back to a bit of the papers thing that you kind of mentioned, I know you had read about 229 papers to this day on your website.
Yeah.
I guess, are there any recent papers about quantum computing that you've read that you found particular interest in that you think will grow in the next time, or just something that had you a little geeked out?
So yeah, what you're referring to is on my website. I keep a list of the papers I read. And
why do you do that?
I do it because I do it for a lot of reasons. Like I think that the way it started was last summer. I had this project I wanted to do, and I had this really clear vision for it. And people around me kept asking questions about it, and I started doubting myself, and I realized like I didn't know like the literature around this paper as much as I should, or like around this idea. So I started doing research to learn more, and I quickly learned like after a week, I had been spending more time reading papers and looking at the background than I had actually spent coming up with the idea. And I was getting discouraged. Like I'm spending all this time reading and finding papers and parsing them and understanding what's going on. I'm not actually doing my research. I'm not actually coming up with new ideas. And it felt bad. Like I felt like I was wasting time. And so I went back and I thought about it. Am I wasting time? Like, no, this is important stuff. I should read these papers. And I realized the problem is it didn't have any candy ideas. It didn't have any reward. Like it was all like stick. Like you need to read these papers so you can do your work. And I should have cared. Like you want to read these papers. And in a way I do that to give myself a sense of completion, which is I read it, I log it on my website, and it's like great. I wrote up a little thing about it. I know I understood it. And also it helped me remember what those papers are and find them in the future.
Yeah, I think I knew for me until really about a month ago, I had no clue what even an academic paper was.
Yeah.
And I always thought that they were like 40 long page documents with a whole bunch of jargon.
Yeah.
I guess, how would you describe an academic paper as someone that's read so many?
Yeah.
Is there a wide variety? And how do you think people themselves can, who may not come from a college educated background, get into reading papers, and why should they even care about that?
So 40 long pages of budget jargon describes a lot of academic papers. Like there's a lot of them which are 40 long pages with lots of jargon. There's a lot of them which are much more than 40 pages with stuff which is like beyond jargon, right? But like you said, like there is a lot of variety. There's also one-page articles which give clear ideas in a very short amount of time. And so if I had to give advice to someone like trying to get into reading articles, is to read review articles, right? So people write papers, and typically when they write them to document this idea that they came up with. And so they want to document it in the most complete in the most clear and the most efficient way possible. And so that means using jargon, and that means writing for the other academics in the room, and that means adding details which are in some sense unnecessary to the key idea, but just to give completeness. And so this is good to have, so you have a well-developed literature, but if you're on the outside, you want to read, you just want to get what's important, it's very bad. So what you should do is, on one level, read books, right? This is how people start to read. You read textbooks. But beyond that, you read review articles.
As in like class textbooks?
Or like academics write textbooks,
okay.
right? Like you have textbooks about up-and-coming fields, talking about subjects of current research. This is a thing. And so if you care about topological quantum computing, like you could read Topological Quantum, which is this book that came out last year by Steve Simon. It's a great book, and it gives you lots of the key ideas in a super digestible and readable way.
Yeah.
And if you want to go to reading papers, you can read review articles. And so that's somewhere between a paper and a book, right? So it's someone who takes in a whole bunch of literature and digests it and talks, kind of gives a survey of what was said. And typically those are much more pedagogical. They're easier to read and they have less jargon. And so those are meant to be read by people who aren't in the field.
Yeah,
that's fair to read.
Something interesting that's kind of happening in the college paper field right now is the increasing usage of AI and ChatGPT to write.
Like by undergrads, like on undergraduate papers.
Which is, I mean, you see an increase in the usage of the word delve in academic particles, and some researchers even copying and pasting the prompt that they put in there.
Right.
How do you feel about that as someone that loves academia and papers? Like, do you think it's a net positive, a net negative? Does it allow researchers to focus more on research and less about writing the article? Just, I don't know. What are your general thoughts on how it's going right now and maybe how it could be with better AI systems?
I don't think I've come across any papers which seem like they were written by ChatGPT, which means either that it hasn't come to me or that it's really well done. So in some way I can't really speak to it in my own life. And when it comes to me writing papers or going to classes, like writing like a midterm or something, like I haven't seriously used ChatGPT, and especially not anything academic. So it hasn't really affected me much. I like hearing other people talk about it and other people have interesting stories, but for me it seems like it's something still in the future.
I think it's hard to kind of use language learning models and something that hasn't really been discovered by humanity just yet. And I think that's really, really key. Does quantum computing have anything to do with improving AI in the future?
Well, these are two such beautiful buzzwords, right? Quantum computing and AI, that there's a lot of papers about it, right? Okay. So like there's quantum artificial intelligence, there's quantum machine learning, there's all these there's different ways of orienting the words which all mean different things in the literature, and I'll have like groups of 20 papers about them, or like more than 20, like a lot of papers about them. I went to like a quantum machine learning virtual conference the other day, so that hear people talk about it.
And was that here in Goleta?
This was online.
Okay.
And my general feeling is that a lot of it is premature, right? A lot of it is trying to do artificial intelligence with computers that don't exist yet, which isn't that interesting to me. Like maybe it's interesting to other people, but currently I'm at the stage of trying to make a quantum computer work. Some of it is very interesting, but doesn't say quantum computers will help the AI. Like for example, there was this quantum machine learning algorithm that had come out where someone said we can train this specific type of model in this specific way very well using quantum computers. This is why we should build a quantum computer. People loved it. And then there was this undergrad at a university in Texas, which came out of a paper and realized that this quantum algorithm, you can move it around a bit and make it totally classical, right? You're going to de-quantize it, and you get this really nice just classical machine learning algorithm out of it. And then there's this sort of spree of people de-quantizing a whole bunch of quantized algorithms. This happens a lot. And so there's a couple algorithms in the quantum machine learning space, which are classical algorithms, classical machine learning algorithms that sort of came through quantum computing. And so this is interesting. There's some real work there, But it doesn't say quantum computers will help us make better AI. It actually says the opposite, right? It says these algorithms are classical.
And I'm sorry if my jargon is off, but is that like taking QNP algorithms and translating them to NP algorithms?
Yeah, so you're referring to like NP as like specific to a really hard computation problem.
Okay.
You're trying like the quantum analog of NP into the classical one, which is not what's going on here. Like,
Okay.
no.
Yeah, do you want to talk a little bit about those? I know we were speaking about them the other day about like NP problems and QNP problems.
Yeah.
I mean, take it away.
So there's this computational class called NP, which is problems that you can't solve efficiently, but you can check that you got the answer efficiently. Like check that you got the right answer. So for example, like Sudoku, it's very hard to solve a Sudoku if you've ever heard. Like it takes a lot of time.
Yeah.
But once you've solved the Sudoku, it's pretty damn easy to check that you got the right answer. You know?
Yeah.
You just look like, yep, it adds up. And that's sort of the hallmark of an NP problem, right? It's something that it's easy to write down. It's hard to write down an answer, but it's easy to check that you got it right once you do it. Unlike, I mean, there's lots of things where even once you do it, it's hard to see, like, is that the right answer? Like, you multiply two really big numbers and you see the product of it. Is that the product of those two numbers? Like, I don't know. Like, maybe it's not the product. You sort of have to do it again.
And what's the benefit of this? Like, why have an entire class dedicated to these type of problems?
Because it happens a lot. Like, there's a lot of problems which are NP, especially in computer science. This is a thing that you keep bumping up against. And so it's something that's useful to describe what we do in quantum computer science if we give it a name. Yeah.
Great. Yeah, you mentioned something about like attending conferences.
Yeah.
And I know, noticing your website as well, you had a lot of these conferences that you had, and you spoke at a couple of things.
Yeah.
How do you find out about these? I feel like it's a lot of people have a lot of interest in a wide variety of things.
Yeah.
And there are many conferences that exist.
Yeah.
But I personally feel like the hardest part is always just like finding out about them.
Mm.
And sometimes I'll do some research and I'll find like 3 that I love that happened like 2 months ago.
Yeah.
Right? How do you keep on top of it? Where do you do to like look up these things? Are you invited to more because you go to them? Like, how can other people get as heavily involved as you are and fall in love with these things in the same way as you did?
Yeah, so the easiest way to get into these things is something like a joint mathematics conference. So this is a conference I went to this winter. And this is the biggest, I guess the way they pitch it is that it's the largest gathering of mathematicians in the world. So there's a whole bunch of people who are either amateur mathematicians, undergrads, grad students, professors, all sorts of different areas, who get together and talk about math. And this is a thing, typically you have to pay, but if you're at a university like UC Santa Barbara, you can find people who will pay for you. So like I went with the Association for Women in Mathematics. Like you can, which is, I'm not a woman, but it's a gender inclusive club, despite the name.
Okay, fair enough.
And they take people who seem like they really want to go to the conference and it really benefit them, and they give them funding to go.
Yeah.
Right. So this is a thing you can.
But how did you even find out to even go through this organization that most people would think I'm not even going to reach out to?
So I already went to Association for Women in Mathematics clubs, club meetings.
Oh,
like I would go there regularly and hear stuff.
Just to meet mathematicians, or?
I mean, it's a club. Like, there's not that many math clubs on campus, and this
Yeah.
is one of the fun ones I like that. And they also, like, I had professors talking about it. Like, it's the largest gathering of mathematicians in the world, which means that a lot of my peers and a lot of the professors, people are going. It's a thing that was talked about in the math world of the people who really like math. And so I went.
Where is this?
And so it changes locations every
Okay.
year. It's typically typically the U.S. or Canada.
And
so here, this one was in San Francisco.
Okay.
Which is perfect for me because I live in Berkeley.
Nice.
My parents live in Berkeley.
Yeah.
And so I could go back for winter break, see my family, and then also go to this conference and have it paid for. So it's a very easy conference to attend.
Yeah. Did you speak at the conference at all?
No, I didn't speak.
Okay, gotcha.
Yeah.
Gotcha. I had a good friend of mine that went, and some of his friends spoke at there.
Oh, fun.
They all finished undergrad at Miami, so they were there.
Nice.
Yeah. So I guess do you find out about this math conference, and then
Yeah.
what happens? How do you do other conferences on top of that?
So other conferences, like here's maybe a typical example. I realized I didn't have any finals on the week after winter quarter, which means that my spring break was going to be like an extra week long. And I was like, I should do something for this week. And so my first inclination was I should go down to Mexico and like Cabo San Lucas or something, like hang out for a week. That'd be really fun.
Yeah.
But then my friends did not have that week off, and I couldn't convince anyone to go to Cabo San Lucas with me. And so my second choice was go to a quantum computing conference. And so there, I just looked up. I'm like, what are the conferences going on? Like, I know myself and I know my field, so I can like look up buzzwords related to that. And then after like 15, 20 minutes of Googling, I'm like, whoa, here's this great one. It's exactly during that week. It's at Canada. It's in this Perimeter Institute, which I really like. It's with 100 people I love. This works perfectly. I'm going to go do that.
Yeah. Let's get off math for a little bit. You mentioned something about going to Cabo, but you were too afraid to go by yourself.
Yeah.
I feel like you would be the perfect person to go solo backpacking. Is this something you've considered, like just traveling around, Europe or Asia by yourself?
Yeah, that I do like solo trips. That's true.
Oh, you do? Okay.
Yeah.
Where have you gone?
I went to like they said last summer I had this internship, and I was I didn't say it, but yeah, last summer I had an internship. I was at a quantum computing company, and that was in Poland. Okay. And so I had a paid trip to Poland for the summer. Yeah. And I was alone, and so I had this whole summer just enjoying myself. And I could have traveled around Europe, but I didn't. I just stayed in Poland, a quick trip to Germany, but then I was mostly there, just enjoying myself and being on a solo trip.
But any desire to just pack everything out, get a backpack, and just travel around, or not really?
It would be fun. Like there's a lot of things that would be fun, right? Like, right. And this is one that'd be really great. It's a general trip planning thing that I don't plan many trips. Like I typically, like, if I have a time just for me to do something, I'll typically do something more academic, because that's just where I am in my life right now. Fair enough. And so when I go on trips, typically it's also an excuse to see someone which I really want to see, or it's other people want to do a trip with me. Yeah. So typically, the group of people is like the inciting thing to do a trip. So that's kind of what's holding me back from doing a solo trip. No, I mean, that makes perfect sense. Yeah. Would you, I guess this is kind of a trip, but more of a targeted trip. Yeah. How do you feel about, auditioning and joining Survivor for a season? Oh, that was fun. I know, you were also on that. We both did a club on campus called Reality UCSB, where we participated and acted in Survivor. Yeah. Any ambition to join the real thing? I've had this ambition for a while to do a reality show, and particularly Survivor. Like, this is really fun. Why Survivor in specific? Well, lots of the other reality TV shows are like dating shows, which could have been fun, but I have a girlfriend now, and so that kind of that puts a damper on the whole thing. And then there's nothing else that has the flair that Survivor does. Like, you just win the Amazing Race. That's way less fun than being on an island. Yeah, against Survivor. So that's why. So if we were to go, what's your go-to strategy, especially that you've kind of dipped your toe in a version of the game? Yeah. What was your initial strategy actually? So you going into Survivor UCSB, what was your strategy? And I kind of want to call you out a little bit, because you voted me out. Yeah. The first opportunity you had. Yeah. And the thing is, we had an unfair advantage because we knew each other beforehand. We did, yeah. And nobody else knew each other beforehand. No one else did. So what was your strategy? What was going on there? No hard feelings. Yeah. I'm curious to hear from another contestant now that, game isn't important. If you want to ask, I can tell you a bit of mine, but I want to hear yours. So going into it, I had this notion that trust was the most important thing in Survivor, right? Like, if people can trust you, then they won't vote you out. If they don't think you're slimy, like, you're not a threat. Mm-hmm. And so trust is most important. And how do you build trust? You don't lie. And if you say that you won't lie, and then you repeatedly don't lie, people will think that you're actually not lying. Then you say that, and then you have a lot of trust, and then you win. And so that was my strategy going. Mm-hmm. I was going to play an honest game. Yeah. And I was going to highlight the fact I was playing an honest game, and this was going to work. That was what I did. And then the first day, we lose. We win our competition the first day. Yes, we do. And then the second day, we lose. Yes. And already here, there's a bit of a lie that happens. It's like the competition is, we're taking this bucket, we're filling in the water. Yeah. And we lose because our bucket breaks. Mm-hmm. And everyone's trying to figure out what happened and why did our bucket break. And I'm the one who broke the bucket. Like, I don't even remember that. Okay, yeah, so you broke it. I broke the bucket. How'd you break it?
Just like
I just hit hard against the sand, like crack. And then when I got back, like people started talking, like, shoot, it's already broken when I got it. Like, I don't know who broke the bucket. It was hard. And so I kind of dispelled it. But yeah, that was already my number one.
Yeah.
And I was like, well, there, like that's not a strategy thing. That was just like,
No, but it is.
Wait, so then after that, I go and I have a moment alone with Alejandro, which is another contestant on our team. And I say, well, I already know Eddie from before. Yeah. So like, me, you, Eddie, me, Alejandro, and Eddie, we're a perfect trio. We can win this. I pitch it to Alejandro. He agrees. It's golden. Yes. We're going to be a trio. We're going to be win. Because there's only 2 other people in the tribe. We can just vote them out.
Yeah.
And then everyone else comes. Eddie, you go to your car.
Yes.
Alejandro goes to change. And that's me, the other 2 contestants. It's me, the 2 people I'm planning on voting out. Right? These are the ups. Right? This is... and we're walking a bit. It's kind of silent. And I'm not sure what comes over me. I say, well, there's 3 of us here. If we make a team, we can vote the other 2 out and we win. And they're all in for it. And so then all my ambitions of a clean game brought the win though. Like we're 10 minutes into strategizing. And I'm already on 2 alliances. I've lied about breaking this bucket. Like there's no going back at this point. And it feels great. Like I have 2 trios. I remain with Eddie and Alejandro, or it can be with Michael and Jesse. And Eddie, I was planning on being on your team. I really was. Like you were the real team. They were the team with the fake team. And then I go to talk to you about the strategy. Me and Alejandro go up, and you waffle. We're like, are we going to be on the same team? We can vote out the other 2. And you're like, oh, I don't know. I haven't decided yet. You know, I'm still pinning down my strategy. And I haven't decided yet I'm pinning down my strategy. It's no, I don't want your strategy. I thought that's what that was code for. Right? I took that as a strong no. I'm like, well, I don't know what's going on with Eddie, but clearly he has some other arrangement. Like I got scared. Right? And so now I'm like, okay, our team is real team. Right? And so we had decided to vote out Alejandro. And so we weren't going to switch it to you. Like we were going to vote Alejandro, and then we're going to vote you out next. And then there's like a last minute thing. Like Alejandro comes to us and says, "Let's vote out Eddie instead." Okay, let's do it. And so like we vote you out, and then I mean it's always a little team of 3. We vote Alejandro out next, and then that's how it goes.
Yeah. But then so you guys vote out me.
Yeah.
Vote out Alejandro. Yeah. Everything worked perfectly. Yeah. Come the merge.
Yeah.
I come back. What's your thought process there?
I was a little bit scared. It's like, oh my god! Like I just voted this guy out in cold blood. You know, he's not going to trust us, right? And like I said at the beginning of the game, trust is the most important thing. Mm-hmm. Like, you know, whether like he likes us or not isn't the important part. He doesn't trust us, right? It would have been nice to get someone like who the other team had voted out, who didn't trust the other team, so they could trust us. But that's how it goes. And you guys were in a middle position where it was clear that you were telling both teams, you know, oh, we're gonna help you, and you tell the other team we're gonna help you, you tell us that you're gonna help us, and then it was just like praying that you would choose us at the end of the day. And at some point you were choosing us. And then you stop. And
was there any point where you tried talking to the team to get out Bella and I in the middle? Was there any sort of moves, or did you guys, you know, kind of pit yourselves against each other and allow us to do our thing?
Well, in my opinion, if the super idol had not been in the game,
okay, yes,
like I would not have gotten out that night I got out, because there was we voted. Like we go to any of the yellow team to vote out, and I had the votes for it. Like we got the right votes, and then there was idle play.
Yeah.
Right. And we're trying to decide who to do, and we saw that there was these 2 very close members in the yellow team. There was a Will and Nick, and if one of them had idle, they would probably get with the other. Mm-hmm. And I had talked to the 3rd member on that team, and he essentially implied that there was an idle in the first 2.
Yeah.
And so I knew I couldn't vote whoever was on that team because they played idle for each other. So I had to vote the guy on the outs, right? And there's no shot that they had 2 idols, right? And then they did have 2 idols.
Yeah.
And he had an idol, he played it, and I went home.
Yeah.
Right? And so I had the votes I got off on an idle play, But even if I hadn't, like now, like retrospecting, like talking to people around, like I would have gone home the next night.
Yeah.
Right. So
Well, I mean,
I would have saved me just one day.
I kind of did some work in trying to make
Yeah.
you public enemy number one.
Yeah.
That was my thing.
Yeah.
People can very easily tell that you're intelligent. So
Yeah.
I was going around telling people that you were smart and
Yeah.
telling them about your math background.
Uh,
And it imposed a bit of fear. And I think that's why I was able to kind of work in the middle, because people feared this side and this side,
Yeah.
and I was just kind of like,
Yeah.
kind of shooting shots both ways.
and on that revote, so it was between me and Bella. Like
Yeah.
it wasn't a close revote. Like everyone voted to have me out.
Yeah.
Like including my closest ally.
Yeah.
My guy who's been with me since day one, Jesse. He voted for me to go home. Right. So kind of that lopsided vote to me really shows like, oh yeah, okay, I was destined to go home. It wasn't just a close I don't play. It was I'm going out.
Yeah. Who did you want to win? Like, if you were to, like, of all the contestants that played, who did you want to win?
I think I said things that Jesse. I think I said things to Jesse that can't be unsaid. Right? Like we're a team. Like we are in this.
Yeah.
And so I wanted. Like if I don't win, he should win.
Mm.
Right? We were a team. I
Yeah.
wanted a team member to win.
Yeah.
Yeah.
Fair enough. Anything else you want to share about that? About Survivors in Santa Barbara? It's just
It was a really good time.
Yeah.
Yeah. Jesse made it to the final three.
Mm-hmm.
Good on him.
Yeah.
I enjoyed my strategy a lot. I had a good time playing that game. If I were to play World Survivor, I'd probably play it different. But
Yeah, fair enough. Now, I guess going back to math a bit, you have reached over 95,000 accounts on MathWorks. What is MathWorks, and why are you so active on it?
it says MathOver Flow.
Oh, MathOver.
yeah.
I'm sorry.
Yeah, it's a really fun site. So it's this Q&A site where mathematicians, which are, I guess it's supposed to be for questions that would be of interest to research level mathematicians, answered by answers that would be of interest to research level mathematicians.
Mhm.
And so this means that it's also for amateur mathematicians, which think they're research level, which is me, right?
Yeah.
And I mean, I got into math in high school, and I had a friend who was also pretty into math, and we did math together, but I did feel apart from the mainstream mathematical community, right? Because I was, right? Like I wasn't talking to mathematicians, I was doing my own thing. And so MathOver was really a way for me to get in contact with actual mathematicians. Like, if there's some math question that I was like burning, that I was thinking about for a really long time, I could go and I could ask it, right? Like, there's this one problem that I spent months on. I was really worked up about this problem. At some point, I'd be like, you gotta move on and do other things, Milo. But I needed to answer. Like, I needed just like the proof.
What was the question?
I mean, it was just like this technical thing in number theory that was, it was just this fun thing which interested me.
Mm-hmm.
And I went and I asked it. I'm like, you probably know I can answer this, but whatever. Let's get it off my chest, have an official answer. Next morning, I look at it as an answer. And it's actually, this is one of my greatest moments in my mathematical career. It was really excellent. The answer came the next morning, and it's from Terence, who's one of like the biggest mathematicians in the world, right? And he stooped down to answer my problem. And so if it's gonna be answered by someone else, at least it's answered by Terence. And he just brilliant proof. And it was just like this mind blowing thing.
Well, describe it. You have to.
It was this proof that, like, he started off with this lemma, which is like a lemma is like in math is some statement you prove before you move on to the actual problem. It's sort of a technical ingredient. And I looked at this lemma, I'm like, how is that whatsoever relevant? It's this crazy technical thing using this machine from Fourier analysis I had never heard of before.
Mm-hmm.
And then he uses it, and pow, he snaps his finger, cites 3 big theorems, and then my problem solved.
Yeah.
And it was just a moment that brought me closer to the mathematical community, exactly what MathOver was supposed to do. Like, me, some random 15-year-old in my bedroom can access one of the world's greatest mathematicians. And it showed me, like, it validated the questions I was asking, because it showed that this was a question that he found of interest. Mm-hmm. His first line was, "This one was rather tricky," which I was like, yes! and it helped show me how, like, abstract machinery that like when you first learn it feels totally unnecessary for solving problems can be really useful for solving the problems you care about.
Yeah.
And
so like Terence Tao, right, is widely regarded as the greatest mathematician alive and one of the greatest mathematicians to ever live.
Yeah.
What makes someone such a great mathematician? You know, like what separates, you know, the average, you know, very, very intelligent college professor, let's say, versus, you know, Terence Tao?
Yeah.
What's the difference there?
Well, there's something that's different, like they're different. Academics are judged in different ways. Like for instance, like Stephen Hawking, right? This is widely regarded as one of the greatest astrophysicists that there's ever been, but he doesn't have that many like influential papers. Like he has a couple interesting things about black hole radiation, but he's mostly known because he wrote these really good popular science books. And he had this cool persona around him, right? And he looked really awesome with that wheelchair. He had a cool voice, and there's this like aura around Stephen Hawking, which made him this really great public scientist. Like Neil deGrasse Tyson, always like not doing any really interesting novel research, but he's like this big scientist in the public eye. And so when you have someone like Terence Tao, this is partially what's going on. Right? He is a big figure in the public eye. He does podcast episodes. He writes really readable books. He has this blog where he writes these excellent articles that people read. He does all this outreach in the mathematical community. You know? I went to the joint mathematics meetings, and like I talked about, and he was a keynote speaker who could deliver things. Like he talks in a way people understand and people like that, and he's this really fantastic public figure in that. And then that's paired with the fact that he does a lot of he spearheads a lot of mathematical movements. Like he has this polymath project, which like, brings in a whole bunch of mathematicians to solve hard problems together in this really cool way. And he has this force in how mathematics is done and the culture in mathematics, which is really powerful. That's another thing people like about him. And then there's his actual research. Like he writes papers and he does things, and he does these amazing things in so many different disciplines and just top level research. So like he's a top level researcher across fields, and he has this powerful influence on the culture of mathematics, and he's a big public speaker who does like very accessible things, and that together makes you regarded as one of the best. Yeah,
and what is it exactly that he's researching? Like, what's his specialty in the grand field of mathematics?
I love how he describes, like you look on his webpage and he has a single word as analysis.
Okay.
Right.
Yes.
So I roughly divide math into algebraic feeling things and analysis feeling things, which is not even subject matter, just how it feels to do. Like something can feel like algebra or feel like analysis, and it's slightly hard to describe, but you know it once you've seen it before. Like if you're a mathematician, I can say, oh, that feels algebraic, that feels topological. Sorry, that feels analytic. That's that divide, and he works all across analysis, which is like that's half of math, right? He really does that's his focus, analysis.
So analysis, there's complex analysis, real analysis. It's this word I keep hearing a lot from all my math friends, but I have no idea what it is. I've had it kind of described to me once before, like in a very simple way. Like, how would you describe analysis? What is it? Why is it useful? And why is it, for you, one of the two kind of roots of mathematics? What is it?
Well, I think a lot of analytic thinking focuses on details within structures. So, like, if you talk about like sort of like the curvature of spaces, or you talk about like the way things interact in a detailed way, like the specific arc that something takes, or you talk about how to solve like a specific equation. There's like a whole bunch of numbers going on. Like that feels to me kind of analytic, whereas algebraic feels like sort of the larger strokes sort of thinking, where you have a kind of you're thinking about the structures that lie underneath as opposed to the details, right? And so it's kind of structural versus detailed thinking in some ways. That's what it feels like to me.
Yeah. Do you have like a favorite problem like from analysis that kind of is you always think about, or just you particularly enjoy doing?
One problem which is key to my heart, which was really influential when I was coming up in high school, is the Riemann hypothesis. So there's these 7 math problems, which are proposed by the Clay Mathematics Institute. They were proposed in the year 2000. They're called the Millennium Prize problems.
Right.
And if you solve one of them, they just give you $1 million. Right? They check the proof is correct, you get $1 million. And when you first learn about this is the instinct is, wow, this is great! Like what a cool way to win $1 million. Like all you do is solve a problem and you get that much money. And then if you're like a mathematician deep into the field, your reaction is, how you solve it just like $1 million? Like it's like this is the hardest way to win $1 million. Right? This is like it's just so not on the level of things.
Have any of them been solved?
So one of them was solved, the Poincare conjecture, and he turned down $1 million. Right?
Sorry, the what conjecture?
The Poincare conjecture. Okay. Like, Henri Poincare was like a French mathematician in the 1900s.
Yeah.
And so he this dude solved the Poincare conjecture. And so not about the money, he turned down the $1 million. Right? Like he was this like, I guess the picture people paint about him in media is like he was this like hermit in Russia living with his mom, and he just spent like 10 years like thinking about this thing which implied the Poincare conjecture. And he solved it using this fantastic method, and he like published it. But like he was thinking about it before they were announced as a Millennium Prize problem. He didn't care about the money thing. The quote is, if the proof is correct, that's reward enough. He's like, I don't really care about the problem. Yeah.
That's a striking quote.
Yeah.
So, but what was the conjecture? What was the question?
So, it's a question in the world of topology, right? So we're kind of coming back to topology.
Yeah.
And it's talking about spheres. So like, there's spheres of different dimensions. Like, maybe the easiest sphere to look at is like a circle. That's like a one-dimensional sphere. And then the next one is like a ball, like what you would typically call a sphere. Then there's like higher dimensional spheres as well. So there's spheres in 4 dimensions, and 5 dimensions, and 6 dimensions, which are very hard to visualize, obviously, but they're easy to mathematically describe. You can write down very simply formulas for spheres in every dimension. And the conjecture roughly say like, if it looks like a sphere, if it quacks like a sphere, it's a sphere. Right? So there's like a couple of key properties that spheres have. It's like, yeah, if you have this property, you're a sphere. And so this is a powerful tool, right? Because if you're doing topology, like all I have to do is check these few things, and then I know it's a sphere at the end of the day, right? And so there's really it's a rigidity about like what sort of things exist in topology. Show that there's not weird things that look like spheres but aren't actually spheres.
And like, would spheres be, I guess, like how are they topologically described, right? As like one short of like, I don't know the term, but like one uniform kind of sheet that like wraps up around each other on all sides. I don't know if you can describe more and like give us some topology background, explain the differences between like toruses and like sheets and the Mobius strip and all that.
Okay, yeah. That's a great question. So like the one sphere, so the circle is, I call it the one sphere. Okay. This is the way topologists talk about it. The way you could describe the circle is that you choose some point in the 2-dimensional plane, and you get all points which are a unit distance away from it. All points which are distance 1 away, that forms a circle. Okay. A sphere, a 2-sphere, like a sphere in 3 dimensions, you just choose some point in 3-dimensional space. So you get all the points which are distance 1 away. That traces out a sphere. And in higher dimensions, if you choose some point in your 12-dimensional space, you get all the points which are a unit distance away. That traces out a sphere. Right? So all the points which are a unit distance away in whatever space. And then all the difficulty comes into like, what is 12-dimensional space? How does that look? And what does it mean to be like distance 1 away or a unit distance away in 12-dimensional space? So that's sort of the subtlety there, but that's what a sphere is.
But okay, so something like that is literally impossible to imagine for the human brain. How do you work with that?
So if you want to visualize it in the same way you visualize a circle or a standard sphere, then it is impossible. But you think about these in different ways, right? And so the obvious question, like the one you start with is, what is dimension, really? Right? How should you think about dimension? And the mathematician way of thinking about dimension is degrees of freedom. So this is the switch you make in your head. Like, if you're in 3-dimensional space, like we're in this room, I have 3 degrees of freedom relative to my position. I can go forwards or backwards. I can go right or left, or I can go up or down. Right? This is 3 degrees of freedom. X, Y, Z direction, and that's why it's three-dimensional space. If you're in something flat, you can go front or back, left and right, but you can't go up and down. You only have 2 degrees of freedom in your position. That's what makes it a two-dimensional space. And so, like on a circle, I can go sort of towards the right or towards the left. I can't go in and out. Right? I can sort of walk around a circle.
Yeah, it's a line.
It's a line, right? And so there's only 1 degree of freedom. Like, do I walk right or do I walk left? So that's sort of, the circle is kind of a one-dimensional object. That's why I think the one sphere. And so what is like a 12-dimensional space? There's sort of 12 degrees of freedom. There's like left, right, up, down, front, back. Then there's another one, and then there's another one, and then there's another one. And so if you think about this as like a space you're living in, what does it mean to live in 12-dimensional space? It's super hard to think about. But if you think about it in terms of degrees of freedom, like your systems become about in our day-to-day life, which have all sorts of degrees of freedom. Like if you have you're doing your taxes and you look at your balance sheet, like there's all these sorts of things. There's like your income that can be up or down. Then there's like your spending that can be up or down. There's all these different degrees of freedom. Like you can move your income, you can move your expenses. If you like your gross income, like your income minus your expenses, that's determined by the first two, right? That you can't move on its own. But these first two numbers, your income and your expenses, you just sort of move those independently. There's 2 degrees of freedom there. And so on your balance sheet, like there's gonna be some number of degrees of freedom, right? Like if you're an accountant, like how many distinct numbers you have to enter to get a full balance sheet. And so like your tax return form, it can be like a 36-dimensional space. Because you have 36 degrees of freedom as opposed to what you enter. And when people look about models, there's all sorts of different numbers of degrees of freedom. Like the space of possible molecules, right? Like a molecule can be arranged in all sorts of different ways. It can be twisted like this, twisted like that. The space of possible molecules is very high dimensional, right? And so because there's systems with tons of degrees of freedom, and just degrees of freedom that aren't just position, it's very easy to talk about high dimensional spaces. And so that's how mathematicians do it, and that's how mathematicians think about it.
So, but like, what are the big benefits of this, and like, why even care about thinking about a 12-dimensional sphere, or a 12-dimensional hypercube, or hypercube?
So like, I mean, let's say you're doing data analysis, right? You have a whole bunch of data, and you're trying to analyze it. Like, typically, like your data is gonna have some number of degrees of freedom involved with it, right? Like if it's gonna be like some table of numbers, like how many numbers is that, right? That's your degrees of freedom. And so your data is actually gonna live in a high dimensional space. And if you want to understand how that data works and how it interacts with each other, you need to understand like how it sits in that high dimensional space. And you need to understand that topology. And so there's this notion like topological data analysis, where you're understanding how things behave in this high dimensional space. And if you do something like artificial intelligence, or in general, is a very big tool in data processing. You have some method for taking a high dimensional space, a space of like very, very big data, and compressing it into a lower dimensional space, lower number of degrees of freedom. And so you can think of this very explicitly as mapping high dimensional spaces to low dimensional spaces. And so this math of high dimensional spaces is extremely relevant for data processing and data analysis, and extremely relevant for AI after that.
Would that be like the equivalent of like projecting a sphere onto a plane? Like, I guess, like making a map of the world. That's something like that, where I mean the sphere to a plane, like you have like exactly you said, the Mercator projection, right, where you turn a sphere into a plane. There you're not reducing dimensions. You sort of are. Like if you like the sphere looks like it should be a 2-dimensional object, but you have this kind of bad embedding of it into a 3-dimensional space. Like you're using 3 dimensions to talk about the sphere, but you really only need 2. Gotcha.
That's why you can project into a 2-dimensional space.
So projections are more I guess they could be more like shifting things into different geometries.
Yeah.
Like non-Euclidean geometry into Euclidean geometry.
Oh, here we're saying entirely Euclidean geometry.
Okay.
But it's it is in a sense changing geometry. It's like different Euclidean geometry.
Right, but condensing, I guess for lack of a better term, like how would one, I guess, take something from like 4-dimensional into 3-dimensional?
Yeah. So like suppose here's how Like maybe you're doing image processing,
Mm-hmm.
right? So your inputs are like pictures of people's faces.
Yeah.
And so this lives in a very high dimensional space. Namely, like for each pixel, there's the red, blue, and green component. That's 3 degrees of freedom associated to every pixel.
Mm-hmm.
So if you have like 256 pixels, then the number of degrees of freedom associated with this is 256 times 30. That's the dimension of the space you're working in,
Mm-hmm.
right? So it's like a roughly like 700, 800 dimensional space. Right? So it's this big space.
Mm-hmm.
But you realize that people's faces like don't randomly live in this 800 dimensional space.
Mm-hmm.
They live on like there's sort of like parts of that 800 dimensional space that all your pictures live in. And the point is like if there's like one pixel right here, which is a given color, the pixel next to it probably be very similar color, right? It's not going to change much, and that's sort of these degrees of freedom are correlated with these degrees of freedom.
Mm-hmm.
They're sort of they're correlated, and they're going to be sort of kind of like 1 degree of freedom together. And so, kind of a very classic tool in this data processing is saying, what is sort of like, this, how can I approximate this 300-dimensional space with a 50-dimensional subspace that captures essentially all of my points?
Mm-hmm.
And then you sort of project onto that 50-dimensional subspace, and you've compressed your data.
Yeah.
And this is kind of what AI does a lot,
Yeah.
is that it finds kind of the lowest dimensional subspace you can put in to well approximate everything that you started with.
So is that where AI is like really going to take over, you think, is in compressing data and still keeping as much information as you can?
Well, this is it, and to a large extent what it does. Like,
Mm-hmm.
I'm not sure that, like, I guess we can get into the architecture of a neural network, but you can really see like if you think with neural network, it starts with a whole bunch of nodes as your input.
Yeah.
Or you need one node for each degree of freedom, right? So if you're in this picture, you have 800 nodes. And then the first step often is you go to the next layer, which has way less nodes, right? Or maybe you stay big and then you go way less nodes.
Mm-hmm.
And when you go to way less nodes, the hope is that you haven't lost all your information. Or the hope is that you still capture a lot of the data of your picture within this, you have 5 nodes within your 5 degrees of freedom. You can compress 800 to 5. And that's your latent space in the language of artificial intelligence. This is sort of like your 5-dimensional subspace. And this connectivity between your nodes is your projection from 800-dimensional space to 5-dimensional space. As you map through your neural network, you've projected down into 5-dimensional space. And you have this really good approximation of your 800-dimensional space.
Yeah.
Coming from the fact that your data isn't chosen randomly, it's chosen from very specific families. Like generically, like, you can't compress 800 degrees of freedom into 5 degrees of freedom. This is a pyramid math. The data degrees of freedom are incompressible.
Yeah. Is there anything with your research that you're looking into with this, or is that just a completely different field?
Well, I think about large number of degrees of freedom because I think about computing.
Mm-hmm.
And when you're computing, like you have a lot of data, and for each piece of data, that's the degree of freedom. Like what can the piece of data be?
Yeah.
So when you have a ton of data, that's the way I think about it. The way literally the way I write down my math is a super big dimensional space. Like if I have 10 qubits, you're in a 2 to the 10 dimensional space. Like you get it multiplies degrees of freedom every qubit you add.
Mm-hmm.
You get this like huge number of degrees of freedom, and so you have a crazy high dimensional spaces, and that's what I think about a lot.
But wouldn't it be infinite? Because isn't the qubit kind of like in an infinite superposition of states as opposed to finite?
Yeah.
Like,
So-
if you have, for example, like 3 bits of information, right?
Yeah.
You have 8 degrees of freedom. How would it work if you have like 3 qubits?
So if you have 3 bits,
Mm-hmm.
right, there's 8 possible states.
Right.
But I would still say you have 3 degrees of freedom. Like, can this thing be a 0, 1? Can this thing be a 0, 1? Can this thing be a 0, 1?
Mm.
Right. And then for your qubit, I mean think back to the balance sheet, right, where you're writing your info and your taxes. Like your income, it could be $5, it could be $6, it could be $7, it could be any number of dollars. It could be 5.1234. Like you can keep on adding decimal points. Like there's infinitely many values you can put in there, and yet it's still 1 degree of freedom, which is what's your income. And similarly, a quantum bit still has 2 degrees of freedom, which is instead of those degrees of freedom only living in 0 or 1, they can be any complex number. Actually, it's a complex plane.
Gotcha. Yeah, that makes a lot more sense.
Yeah.
So it would be like you could either have 0 to however
Yeah.
many dollars, or even negative if you're in a
Yeah.
bad situation, or you can have dollars and no dollars.
Yeah.
Gotcha.
And so definitely you say like in the case of bits where it's dollars and no dollars, it's sort of the terminology like your degrees of freedom are valued in the set 0, 1. Like this is where your degrees of freedom live. They're in 0, 1. Whereas in the quantum case, your degrees of freedom are valued in the complex numbers. This is like where your degrees of freedom live.
And when you mean set, is that like kind of using category theory there? I know you've done quite a bit of category theory stuff.
Yeah, so category theory is a branch of math that I think about. This I'm not saying category theory.
Okay.
This is a classic thing. Like I'm using linear algebra here.
Oh,
like I'm talking about a vector space over Z2 versus a vector space over C. That's what I'm talking about. Much more than right now.
Yeah. Would you like to talk about category theory? And I guess you're just burning interest in it. And what is it?
Yeah.
What is it? What is it used for? And then just get as nerdy as you can get.
Okay, it's a field of math which I like a lot. It is to a large extent like kind of as algebraic as you can get. Like Terence does analysis. I do algebra. And if you kind of keep going in algebra, in my mind, you get to category theory, where like algebra is supposed to be a structural analysis of your problems, and category theory is very much in this structural analysis. And so, I mean, we've been as a society or like as a species, we've been doing math for a very long time, things that look like math, and this has really ramped up in the last couple hundred years. It's ramped up even more in the last couple of decades. And that's about enough time for things to start rising to the top. Like, what are the most important structures in all of math? And we found that one of the most important structures is composition. Right? So if I kind of like transform an object once, and I transform a second time, I can compose those to get one bigger transformation. And like if I have like a Rubik's Cube, I do one move, I can compose it with a second move. I do a first move, then second move. Right? I can there's one move which is like raising an arm, and there's one move which is like twisting my hand. I can twist my hand, then raise my arm. That's a new move I can do. And to this you can compose things. And composition is very universal. So like whenever you have transformations on anything, you can compose them. And so category theory is this abstract language of composition. And there's an implicit statement, when you define the abstract language, and the implicit statement is that this language is useful. The reason it's useful is because it's universal, right? There's a lot of things where you can compose, and it's powerful, and it's expressive, I guess. Like lots of things can be expressed in terms of composition, right? Like if you want to talk about like dimension, right? This is going to be some complicated statement. Like you can think about dimension in terms of composition, right? And so you can reinterpret that concept in terms of composition, and you can reinterpret a lot of concepts in terms of composition.
Meaning, like, for example, like lifting your arm can be one dimension and twisting the thing another dimension, because you have 2 degrees of freedom there. That are
it's not that straightforward of a thing.
Okay.
It's a more subtle interpretation. But in general, like you can rewrite lots of things in terms of composition, and it makes composition a good universal like organizing principle for how you do math, and especially as an algebraist, it's something I find useful.
Yeah. So but then how is category theory how is algebra a derivative of category theory?
I'd say algebra, like it says, is this more structural analysis of the world, and this is a structure you can place onto something. Like you can say, well, there's all these details of how exactly a hand moves, how things work. I'm going to sort of forget about the detail. Like I'm going to forget about what a hand is. I'm going to forget about how hands move. I'm only going to remember how the movements of hands compose of one another. I'm only going to remember composition.
Okay. Yeah.
And somehow I expect to still be able to do math. And this is a more like this is algebra. This is you're forgetting details. You're just doing a structural analysis.
Yeah. I guess here's a fun question that might be a little hard.
Yeah.
I know there's I think Feynman maybe, a very famous lecture, I think, where Feynman goes from counting to calculus.
Yeah.
Right? And I think he calls it elementary in the sense that you have infinite intelligence, you can understand it, right? Could you maybe do something where you go from counting to category theory?
This is actually a very famous little jump, actually. That John Bayes has this kind of by now famous article where he does exactly this. And he actually, it's so good that you realize, or at least it realized for me, that it's actually go from categories to counting. Like people like the thesis sort of is that implicitly what like hunter gatherers or farmers were doing, you know, in the BCs was kind of implicitly they were using language, but they were doing category theory. And then the big breakthrough of mathematics was to stop doing category theory and just start actually counting instead. And then you went from category theory to counting.
Yeah, can you describe that?
Yeah. So suppose you have sheep and you're a sheep herder, right? Here's a category we can consider. So the objects in our category are collections of sheep. Okay. And a transformation is a way you can move those sheep around. Right? Okay. That's it. The objects are sheep, the transformation is where you can move sheep around, you can compose moving sheep around.
Yeah.
Right? And suppose you have two farmers that say, you know, I think, you know, like they were doing some trade, and they're like, oh, I think we made an unfair trade. Unfair trade. I think you have more sheep than me. Let's compare. Who has more sheep? Right. This is a question to ask. I think if you're into BCs and you haven't gone far into math, how do you decide who has more sheep? You put them up next to each other, one by one, and then you see like who has more. Like someone's gonna have sheep left over. Whose line is longer? Yeah. And so this, or maybe to show you the same amount, you want to show that the lines are exactly the same length. And so really what this is you have some function from your sheep onto the other person's sheep, where you're transforming your sheep into theirs. You're saying, oh yeah, that works, right? And so you have sort of this bijective function between the sheep. Like I can assign my sheep to that sheep, that sheep, that sheep. Have a bijective function between them. And if you have someone that's more, you have an injective function. Like I can assign my sheep to your sheep, and you have some left over. That's what an injective function is. And then the surjective function is I can assign my sheep to your sheep, and like I actually have I have extra. Like I can assign double. And so kind of this concept of less equal or more, you have to kind of do in terms of these injective, bijective, or surjective functions between collections of sheep. Right? That's what you're doing. And then there's this amazing advent. Like, holy shit, we can count. Right? Like, I take my sheep, I'm over here, we don't have to move them around. I can just count my sheep. Yeah. I see that I have 12. You count your sheep, you see that you have 12. Okay, we have the same number of sheep. Right? And this is an amazing thing because suppose you're in two different kingdoms. Like, you're not going to move your sheep all the way up. You can just send a little letter of the number. Yeah. Right? And then you can actually communicate. And it's an amazing thing. Like, you don't have to think about individual sheep and ways of moving between them. Right? You can forget this whole active functions and composition. You can just write down numbers and count. And then this is like a really compressed, really great way of doing language. And so, I mean, this is the thing people have to think about. Like, you know, like if you go to the hunter-gatherer tribes, like you have a word for one, you have a word for two, you have a word for three, you have a word for five, nothing. And then you have a word for like more than three. Yeah. Like there's no word for four. Like because you think of three not as a number, but just as this concept of having three things. And it's subtle that you can have these concepts going on forever, and there's an efficient way to take a collection of things and write down that concept. Like this is a non-trivial mathematical breakthrough to get to counting. Yeah. Right? And before people are thinking about sets and functions between them, to talk about less, equal, or more.
And I guess when it comes to like counting, one of the biggest breakthroughs in counting is coming up with the number 0. Yeah, yeah. And you had mentioned something in your website about 0 being your favorite number. Can you talk about that? Like, what does that even mean? What was that hypothesis thing that it was kind of working on? Why? What do you mean?
So, I mentioned before that my favorite problem is the Riemann hypothesis. Right? This is one of the Millennium problems. You get $1 million if you solve it. And this my favorite number being possibly 0 is related to this Riemann hypothesis. Right? And so, here's how this story goes. Yeah. So, there's people trying to understand the Riemann hypothesis, and they ended up coming up with this number. And so this is called the Debrogin-Newman concept because it was kind of shown to exist by these two mathematicians, Debrogin and Newman. And this number is at some value, it might be like negative 12, it might be like 4.35, like it could be like, it's going to be some number. Yeah. And it controls and tells you how true the Riemann hypothesis is. So if this number is negative, the Riemann hypothesis is true. If it's positive, the Riemann hypothesis is false.
Mm-hmm.
And if it's 0, like you're on the line, it's true at a 0, but just barely true. Like it's almost positive, but just barely true. And so people, the first proof was like, yes, it's like maybe this was the second proof, and it showed that it's like greater, like negative, like trillion, billion, like okay, it's like it's less than this really big number.
Mm-hmm.
And then people found like, oh, it's less than like 5. Oh, it's less than 1. Oh, it's bigger than negative 12. And they're like sort of honing in on 0, and hope that either eventually you're going to show it's 0 or less, which is what the Riemann hypothesis, or you show it's bigger than 0.
Mm-hmm.
And so it turned this Riemann hypothesis, this binary question, to true, not true, into sort of a more continuous degree of freedom of how true is it, right? And so to me, it's this fantastic question. Like, it's this number, like it's somewhere. Maybe it's 0.1.
Mm-hmm.
Maybe it's negative 0.1. Like, where is this? Where is this number? It's somewhere.
Yeah.
And we know it exists. But we can't approximate it. We don't know. Like, it could be like some rational number. It could be some weird number. Like, we don't know where it is. And then people keep finding better balance. Like, people keep proving like, oh, it's less than 0.5. Oh, and then like, people are like, it's bigger than negative 1. It's bigger than negative 0.1. It's bigger than negative 0.001.
Yeah.
And then Terence comes into the picture. We talked about it before. He proves it's not a negative number.
Oh.
Which does not resolve things, because it could be exactly 0. And if it's exactly 0, the Riemann hypothesis is true. And so like the title of this paper is like, if the Riemann hypothesis is true, it is barely so. Because like kind of the negatives was like it's very true. Just like it's half on the cusp of true and false. Which is in part like a motivation for why the Riemann hypothesis is such an interesting question. Like it's something which is barely true. It's barely true.
Is it possible that it's not 0 but infinitesimal 1, where how 0.9999 repeating is 1?
Yeah.
Right. So 0.000 with a 1 at the end is 0.
Right.
But is there in any sort of sense here where it's like it's not 0 but it is 0?
Yeah. So this is one which exists in different areas of math. These sort of infinitesimal differences, which are things which are like 0, but it's not. Not in this case. Here we're talking about standard, it's real numbers.
Okay.
It has to be 0, or it's not 0.
What do you think? Do you think it's?
I think the Riemann hypothesis is true. Yeah, I think it's 0. So I conjecture. So the way I phrase it on my website, I think it's funny that my favorite number is the Debye-Newman constant, and the big conjecture that you get a $1 million for solving is that my favorite number is 0, because we proved that Debye-Newman is 0.
So and then what is the Riemann hypothesis? Exactly.
So,
what is it stating? What is the question?
Yeah. So it's this problem in number theory. So understanding how numbers work. Yeah. So in the way the Debye-Newman constant and the Riemann hypothesis sort of controls how numbers work on some fundamental level. And so I guess I'll tell you I'll tell you what the Riemann hypothesis is through some history.
Mm-hmm.
So people want to understand primes. This is the building blocks of numbers. And so people define this prime counting function. Like you give me some bound, and I say like how many prime numbers are there left in the bound? Right. So my bound is like 20. I say okay, 2 is prime, 3 is prime, 5 is prime, 7 is prime, 11 is prime, 13 is prime, 14, 15, 16, 17 is prime. That's all the fun.
And 19.
And 19. Okay. And then I would count this up, and I would say like that's how many are less than 20.
Yeah.
That's my prime counting function at 20. That is prime counting function. And Gauss, a very famous mathematician, wrote down the values of his prime counting function. Let me look at how it grows. Like, how many prime numbers are there? Like, if you give me a bound, how many prime numbers should I expect that are less than that number? And on some level, you might expect primes to be super random. Like, sometimes there's a whole bunch of primes, the prime function is big, and then it doesn't grow very much. There's not that many primes. But what he found is it's very, very regular. Just grew like this lovely curve. Like this nice kind of, it wiggled a little bit, but it's a pretty straight curve. And it looked exactly like x divided by the logarithm of x. So how many primes are less than x? About x divided by the logarithm of x. That's about how many. And that's just, it is what he observed. And then after a while, he and some mathematicians say they proved it. And so they proved that sort of, it's number of prime less than x is approximately x divided by the natural log of x.
Is there any reason for that?
there's a lot of, I mean, there's some deep reasons. Like there's some deep reasons.
Uh-huh.
And what's interesting is that they proved that it was approximately that. But in an experiment, like if you actually just plot the number of primes less than x for a whole bunch of values, less than a whole bunch of bounds, you see like it's scarily close to x over log x. Way closer than they proved. Like they proved it's sort of close, but it's close, right? And so that's the Riemann hypothesis. The Riemann hypothesis, like, it is close. It tells you kind of exactly how close it is. Like it is, it gives you that bound. Like this prime number, like this theorem is known as the prime number theorem. Like this estimate given by the prime number theorem, that the number of primes less than x is approximately x over log x. This estimate is tight. It is good. It tells you how good it is. That's the Riemann hypothesis.
So it's basically saying like this is a distribution of primes, but the real world is like the roughed up version of this. Is that what it is? And if you were to
we know it's a roughed up version, but it tells you how roughed up it is. Like it's not that roughed up. And this is like, and if you prove the Riemann hypothesis, it gives you a whole bunch of other theorems in number theory. And it sort of says like if you have like there's all these estimates that we know are true, like this thing's approximately this thing, but it tells you that those approximates are really close. Like when all of these different like approximations of number theory, which we think are like kind of true, are really true, and so this helps. Like apparently like number theory is more exact than we can currently prove. In number theory, like typically your error is like 1 over x, your error is like 1 over root x. Like you have this big improvement over how big your errors are. Yeah.
Are there any? So other than this one, are there any other Millennium problems that you find a big interest in that you would love to solve, or are they just too difficult to even like fathom thinking about?
No, I fathom thinking about them. I like to think about.
Is it the money or is it the difficulty that particularly inspires your interest there?
What I like about them is it gives a list of just like these problems are important. Like these are like you should care about these problems. Everyone else should care about them. Like I was talking to the guy who wrote the list and who invented the problem every day, and he was saying like that this like I was kind of the target audience, like young mathematicians getting into it. Like we're like he wants to like inspire that generation, and it works. Like these are big problems. And so Riemann hypothesis then I sort of switched my mathematical lens from analytic number theory, which is where Riemann hypothesis lives, to algebraic number theory. So I knew I liked number theory, but I switched from analysis to algebra. And then I got more into the Burstyn-Swanerton-Dyer conjecture. That's a different one they have, which is it's less about because here you can see analysis. Like it's about estimates, right? Does this thing grow approximately like this thing? What's the error? That's very analysis. This algebraic thing is like much just like cleaner. Like this thing is this exactly, and I like that one a lot. It's a very nice conjecture. And nowadays, I probably think the most about Yang-Mills and the existence of mass gaps, which is sort of a mathematical physics one. And so again, like the guy who came up with these problems, he's a mathematical physicist. That was his favorite problem on the list. But he also thinks it's the hardest one.
What makes the problems so difficult to solve? Do they just require a brush of elegance that allows you to solve the problem, or they're just notoriously what makes them so difficult? Why attach $1 million to a math problem?
So, I mean, maybe you have the thing that makes this the most obvious is that there's a lot of math problems. Some of them are going to be harder than others. You're going to have some that rise to the top as being not only do people find hard, they can't even find footholds. Like these are far away, and not only are they far and people can't find footholds, but they are important. Like the Riemann hypothesis, that one it gives all these new estimates in number theory. Like people really want that. Like Burstyn-Swanerton-Dyer conjecture, this tells you how L functions work. Like we can get L functions bound so good if we can solve that. And Yang-Mills exists to mass gaps. This tells us we can actually do math on quantum field theory. Right now we can't really. These are important problems, but they're super hard and we can't get a foothold on them. And these problems are gonna exist. People are gonna think about the things they care about, and eventually they're gonna get stuck. And some people are gonna get more stuck than others. And so they sort of collected those people who got super stuck and having some big problem that just can't solve.
Mm-hmm.
Yeah.
Yeah. How did you get into contact with the person that wrote the problems?
So there's a professor I really like at UCSB who taught me topological quantum computing,
Mm-hmm.
and as a gesture of thank you, I wrote his Wikipedia page, because he seemed like he should have had a Wikipedia page, but he didn't. So I wrote. So this was Zheng Hunwang, and I wrote his Wikipedia page, and it was really nice, and he liked it a lot. And then apparently he was at some conference, and his friend read the Wikipedia page and really they saw like that's a good Wikipedia page. Where do you get that? And you're like, oh, this was a student of mine did it. And so the friend was like, do you mind if I have him revamp mine? Because like he didn't like his Wikipedia page, and I was like, I wrote the Millennium prize problems.
Yeah.
So he's like one of the chair of the Harvard math department, he's president of AMS and all that. But he wasn't really satisfied with his Wikipedia page, and so he reached out to me. He sent me an email. I was like, could you write my Wiki page?
And did you write it?
And then I read it. Like we had like some Zoom chats, and like it's cool. Like he gave me this look into his career, and like talked about the highlights and like things that he found important about what he's done. And so I could like restructure the Wiki page and especially talk about his research and what he's done for his life. Yeah.
Well, that's really cool.
So it was a fun experience.
Yeah. I guess I think something that I find really cool is just your story of graduating after 2 years and then going to Caltech for a PhD straight out of undergrad. How does someone do that? How does someone go from let's just say middle school? Because I imagine that's probably where things started ramping up.
Yeah.
How would somebody else that's listening right now that really wants to graduate soon and get into research as quickly as possible?
Yeah.
How would you advise someone else to do what you did?
Yeah. So most people take 4 years to do their undergraduate degree or study more. I did mine 2 years. This isn't very typical. Like even like I'm at UCSB. I'm also within this smaller program. It's called the College of Creative Studies. UCSB is divided into 3 colleges: letters in science, engineering, the College of Creative Studies. The College of Creative Studies is much smaller, and that's where I am. And even in this program, wasn't standard. Like I'm the third student in the history of the college to have done it. Right, so this is not how it goes. And there's a lot of things that went right into making it happen. I didn't have the vision that I was going to do this from day one. I knew that this was a possibility, but it wasn't clear throughout the whole thing that this was the right choice for me. And so if you are in middle school, I don't think you can confidently make the assertion that you're going to want to graduate in 2 years. Right? There's too much uncertainty.
Yeah.
Like if even like me, like in college, I couldn't make that decision until relatively late. So I'd say as a first step, like be far enough in your career that you know it's actually something you want to do. And then by that point, for most people, if you've already decided that's what you want to do, there's things that you've done which will make it impossible. Like maybe you'll be at a big school with a big bureaucracy. And big schools with big bureaucracies are hard to manage. And maybe this is something that's just impossible at your school. It wasn't for me. Right? Like I was in this small program where there's a very small bureaucracy. Like the people who let me graduate is the steering committee of the College of Creative Studies, and the steering committee for math specifically, which is a group of 7 mathematicians, which had to get together in a room and decide to let me graduate.
Yeah.
All right. That's who has to do it. And so it's a much smaller thing. It's just much more possible. And so I guess that's the first step. Like if you're in middle school, like there's a lot of things to optimize for. You shouldn't optimize for graduating early.
Okay.
Yeah.
Yeah, but even just coming in here freshman year, fall quarter,
Yeah.
taking graduate level courses.
Yeah.
Like, what's that process to do that?
So I guess maybe I'll just kind of start from middle school. Right?
Okay. Yeah.
Like in 5th grade, I had no inclination that math was anything special. I didn't know anything about math. Like I did math class. I thought it was fun. I didn't realize you could have difficulty with math. Like all of my friends got math pretty easy, so I thought it was like, I don't know, like they introduced slowly enough that by the time they actually like introduced something, I already had a good picture of what it was.
Yeah.
And so I thought that they weren't teaching me anything new. It was like stuff I already knew, and they're just like reminding it to us. Like, oh yeah, I remember that, and I was like, it was just a fun time with my friends, and so I was really surprised in 6th grade when my teacher said like, oh, you're really good at math. Like, Is this like
What does that mean?
Are people not?
Yeah.
And they're like, yeah, you can do like advanced worksheets. I was like, what do you mean more advanced? They're just like, don't we already all know this stuff?
Yeah.
And then she would give me these advanced things, and then she would talk to me, and then it kind of decided like, oh, there's this world I can go down. And so like during class, I would like puzzle through things, and I remember like I kept discovering these like cool nifty facts about numbers. I was really enjoying math class, but at that time I had no interest in being a mathematician. Like I wanted to be an animator at Pixar. I wanted to animate movies. Maybe like do some R&D on that, because I thought like, oh, there I could like use some math, you know, like doing R&D in movies. But I want to be an animator. That was the path. And then in 7th grade, we moved to a different school district. In this school district, not only do they have like, you know, you can talk to a teacher to do some advanced math, they actually have like advanced math classes. Like you can skip grades. Like you can, even as a 7th grader, be doing 8th grade math, be doing 9th grade math, be doing 10th grade math, right?
Yeah.
Well, there's one kid in the whole school, 7th grader, doing 10th grade math. So it was a rare thing. This was the exception. And this is like, it slowly worked his way up to that all through elementary school. But there's one kid doing 10th grade math. And I show up. I'm like, great, let me put me into 8th grade math. I'm going to finally do advanced math. That'll be great. And I go into this, I'm like, this is the wrong room. This is not advanced. I already know all this stuff.
Yeah.
Like, I was placed in the wrong thing.
Yeah.
So I went back and I argued my case that same day to the administrator. And okay, we can put you in 9th grade math. They put you in 9th grade math. And I'm like, what is this? I already know this stuff. And so I was like, put me in 10th grade math. They're like, no, you don't understand this. This other kid had to spend years working up to this. No. You can't go to 10th grade math. So I was like, well, what if instead of one of my electives, I do 9th grade math and I do 10th grade math? Would you let me do that? And they're like, well, that'll be difficult for letting you graduate and all that. Like, well, I'm going to a different school district anyways after this. Can you please let me take 2 math classes? And they said yes. So I took 9th grade math, I took 10th grade math. So the 10th grade math was geometry. I got a C the first semester of geometry. This is or first quarter of geometry. This is the only C I've ever got.
Yeah.
And yeah, it was tougher. Like it was at my level.
Yeah.
And
So your level is 10th grade math.
So my level was 10th grade math at that point.
No, it still is, right?
And so I enjoyed that a lot.
Yeah.
I had this great time. I learned a lot of math. And then I came back to my school district, because we had it was like a sabbatical, like we went away for a year.
Yeah.
And then I go back to the school district where I was before, where you cannot skip grades. They put me back in 8th grade math. And so I'm like, this is dumb. I'm like, whatever. I don't want to do math anyway. Like, I want to be an animator or work at Pixar. I don't need math. Yeah. Right? I'm done. Like, that was fun. I enjoyed doing advanced math. I'm done with this. I think partially this is an East Coast, West Coast difference. Like, the school I went to that 1 year was on the East Coast in Maryland.
Really?
And they had this idea of excellence, right? Of like wanting to take their students so they were really excellent at their subjects.
Yeah.
Whereas in the West Coast, it's in Berkeley, California, we have this attitude of no child left behind, right? Which is more like not about skipping, about like helping people who are struggling the most. And I think to me that cultural difference seems really important in being able to skip to 9th grade.
Yeah, no, I never thought about that. Yeah, because I spent all of my thing in Southern California, which, is even more of that kind of thing.
Yeah.
The Bay has that sense of competitiveness and let's advance things, but Southern California, especially where I was pretty calm.
Yeah.
Oh, so you would say there's a difference between East Coast, West Coast culture when it comes to academics?
Yeah.
Does that translate over to college as well, would you say? Or is that mostly more of a pre-collegiate thing?
Well, I was in the middle of a story going into 8th grade, but I think it does translate to college as well.
Oh, I'm sorry, continue.
Yeah. So then, I at this point still want to be an animator, work at Pixar, and then I had this experience, and it's funny, know what happens later, but I had this experience where I go and visit Caltech. So my older brother is doing college tours at this point. This is the first college tour he does. He goes to Caltech just to get started. What does college look like? And I went with him, and I was enamored. It is an amazing school. I loved everything about it. And I told my dad, I was like, I'm going to apply to Caltech to be, a mathematician and be a math major. and I'm also going to apply to Savannah College of Art and Design, art school.
Mm-hmm.
I'm going to get into both, and I'm going to get the Caltech just to show that I can. And then I'm going to reject it and go to college, go to art school, right? I'm going to do it just to show I can. And he was like, Milo, if you get into Caltech, you should go to Caltech. It's a really good school.
Mm-hmm.
And I was like, yeah, you're right. This is such a good school. And I was thinking about it like the next day. I was like, wait a minute. That's right. It is a really yeah. Going to Caltech would be so much better than going to art school. But wait, if I went to Caltech, I wouldn't be an artist anymore. I'd switch to being like going to math. I guess that's what I want. Like I was like thinking for I was like I'm imagining going to Caltech, and that just sounds better than imagining going to SCAD. Yeah, I want that. And so I guess I want to do math. Like I don't want to be an animator. Like the dream of math sounds better than the dream of animation now. And so I flipped the switch. And I like introspecting there. And I want to do math.
And did you get into Caltech?
I did not.
Okay.
I got rejected undergrad.
But I imagine what you did now is probably even more impressive than.
So now I'm going grad school there.
Yeah.
So it kind of comes full circle.
And at 19.
At 19.
I guess you'll start at 20.
Yeah, I'm about to turn 20. Yeah. And then yeah. So at that point, I decided to be a mathematician. Like I already knew multivariable calculus. I was were really strong. Like it was just smooth sailing. Like I learned a whole bunch of math. Got really into my own. Like I did some formal programs. Like I went to the Berkeley Math Circle for a bit. That was nice. I talked to a few professors who taught me a few things, but mostly I watching YouTube.
Mm-hmm.
I was reading Wikipedia pages.
What YouTube channels were you watching?
Like
Numberphile.
Like these videos where they would solve integrals fast, big integrals.
Oh, like the MIT integral videos?
MIT integration B and
MIT.
And there's flammable maths where they would have it's some big integral of e to the x over x cubed minus 5x plus 6 times the gamma function. It would do this big thing. And I was loving it. They would expand out and they would, because that's what I knew. I knew calculus, right? That's what I learned. So I knew how to do integrals, and I just watch it. And I got really into doing just complicated integrals. Like if you go to YouTube right now, there's a video that I submitted. Like they did a viewer submission process where you could submit and get your own video posted of
for what?
Of solving an integral.
So is this just you uploading a video to YouTube?
No. So this is me on the Flammable Maths YouTube channel where they have this guest appearance.
Yeah.
Featuring 15-year-old, 14-year-old Milo.
Yeah.
Solving some big integral. I think it's 14. And now I was like, yes, I got selected. I'm so cool. That's what I sent to.
Yeah, we'll link it below.
And from integration, you can go so far in math. You need to use the technique of residues. You need complex analysis for that. And then you want to integrate these special functions. You need to learn a gamma function, and there's a zeta function, and there's all these things. And if you have a zeta function, you can learn about the Riemann hypothesis, and you can reinterpret it using line integrals, and then you get pretty deep just based off calculus and integrals. And that's kind of what I was doing for the first 2 years or so. And I started asking these really tough questions based on that, and that's kind of analytic number theory. That's how I got there. Yeah.
Do you this is very, very different topic, but do you use any sort of your love for math or brain for math and some of your thought processes and philosophy and religion? I know there's something that you want to talk about. Now, is there anything with math that kind of ties into any of that, or is this just two different sides of your brain kind of working? Like I know for me, I'm really big into STEM as well, but I love my performing arts, and to me they were two different things that didn't really cross over much, but they allowed my brain to grow. Are you applying one thought process to another, or are they two kind of separate Milos all encompassing the same body?
Obviously there's a relation in the sense that math informs how I think, right? I think like someone who was raised on mathematics, right? And that influences the way I interact with religion, certainly. And then the way I grew up interacting with religion is that I didn't really. I grew up in Berkeley, California, and it was an atheist town. Like, my parents didn't believe in God. None of my friends believed in God. I wasn't close to anyone who did. Like, I'm not sure if I talked to a theist, really. Like I just had this notion, like, of course God doesn't exist. Of course there's no higher power. Of course everything is just governed by the laws of physics. And if you want to understand how the world works, you don't turn to spirituality, you learn to turn to science. And that was kind of obviously the truth.
Mm-hmm.
Everyone believed that, except if you were like a weird religious person. I had no conception what that would really entail.
Yeah.
And so certainly that's influenced like my interactions of like math and physics, because I saw math and like and physics and science as being like the be all end all of how the world works, right? Like I didn't like if you grew up religious, certainly like art is a way you mediate your experience with the beyond, and so art is a way to interact with what's true. Right, it's a way to interact with that, and so that adds an emphasis to art, which I didn't have. Like to me, art is totally peripheral to understand the way the world works. So certainly they influence each other, but beyond the fact that they both influence Milo, and then that's two different parts of me, like it feels pretty distinct.
Yeah. Great. Well, it was really great talking to you, and I really appreciated having you on.
Okay. Yeah.
Any last words you want to say?
I mean, this was great. Thank you for having me. I really enjoyed in talking with you and saying what I want to say. It's great.
Yeah, I wish you luck in your summer and your PhD in Caltech and then beyond. I'm really excited to see what you do.
Great. Thank you.
Yeah, thank you.
Great.